All right, so we are ready to go. So we are done now with exam number 1, chapters 1 and 2 in the books. What we're going to do today is we're going to introduce chapter 4, which is where we get to our last little pieces that we need to do inferential statistics. So we're going to take a look at probability specifically, the way a statistician thinks about probability, but we're now working our way to the final sort of end game before we get to do inferential statistics. On that note, I will be posting up all future assignments in the next couple of days, probably today and tomorrow. I'll get those up just in case you're wondering, are we ever doing anything again in terms of assignments and homework? Yes, we are. But just wanted to make sure that we all focus on exam number 1, not worrying about what's coming up later, because these are the fundamental skills and strategies that we need to be very good at before we ever move on. So today's class is going to be reflective of that, where we just introduce the idea of probabilities, make sure that it sinks in, take the time that we need to make sure that we have that solid foundation. All right, so what we're going to do now is we're going to turn to chapter 4, some key ingredients for inferential statistics, and the key ingredient that we're going to focus on is probability. So it mentions inferential statistics. We are very close, very, very close to doing the cool stuff in psychology, doing the tests on real psychological data where we answer real psychology questions. We're very close to that. We just need a couple of more steps. So now we're going to focus on that last little aspect that we need, which is probability. So we're going to make sure that we practice about probability, that we get it all done. You've been putting in a lot of work up until this point, and we are now right at the cusp of doing the inferential statistics. So this is what we're one of the last pieces we're going to need in order to do that. Now, just to sort of put this into context, I kept mentioning about how inferential statistics is the power behind psychology, how that is what opens up psychology to the world, rather than just keeping psychology as a science that is only for the elite, right? Only for the people that can afford it, and not for humanity in general. Inferential statistics makes it for humanity in general. And I'll give you an example. So let's say that you graduate here, you go to graduate school, and you work with special education. You work with clinical psychology, education for children with special needs, and let's say that you focus on autism. After you graduate and get your degree, you become a psychologist that works with autistic children. Let's say that you're working with these, I believe, 12 autistic children in a particular class. So you're working, and they call you into a class, and you're looking at this class, and because of your training, because of your knowledge, you think up a new way to teach these children. You think up a new technique, and you say to yourself, all right, I've devised this new treatment, this new way of educating these students. It's a new program that I've devised. It uses, you can do it on a tablet, uses that technology, uses these particular theories that I've learned about. It's a new way of teaching these students. And you want to know, you're going to test it out on these 12 students, and you want to know, will it work for these 12 students, right? Will it improve their learning outcomes? So let's say that you try it for a semester, and lo and behold, these 12 students learn more than an average student would. These 12 students on your program do better than previous students did on the old program. It's great. That's wonderful. But without inferential statistics, that is where the story ends. All that you would be able to say, all that you could intelligently say, and all that you could ethically say is that your treatment works for these 12 students and these 12 students alone. And you would not be able to help a single other person other than knowing that your technique works for these 12 students. Without inferential statistics, that is where psychology would end. And the people that would benefit from psychology would be the extremely rich who could hire personal psychologists to work with them and work with their children and work with their individuals. Thank goodness we have inferential statistics, because inferential statistics is what lets us go from a sample of 12 students, a sample of 12 autistic children, and then intelligently and ethically draw conclusions about the population of autistic children. And once you can draw conclusions about a population, when somebody reads your research and says, oh, I have an autistic child that I'm working with, do you think your program will help him? Instead of telling this individual, well, I have no idea. It helps my 12 students. I have no idea if it'll help your student. Instead of having that answer, because of inferential statistics, you can say, you know what? My program works for the population. So yes, it will help your autistic student. And yes, it will help these two other children. And yes, it will help this child who is doing that prototypical autistic stacking of cups. And yes, it will help this child who is not engaging in cooperative play. It will help the population of autistic children. And that is the power of inferential statistics. It opens up psychology from just being able to do things about a sample to being able to impact the entire world, the entire population. So that's massively important, and that's what we're building towards. And we have one final little piece that we're going to look at and introduce today. So today we're going to have our introduction to probability. We're going to take a look at probability and frequency distribution. So there they come back, frequency distributions once again. You're going to see that the way that statisticians think about probability is very different than the way that a mathematician thinks about probability. If I say the word probability and you're kind of cringing a little bit, it's probably because you're remembering math probability, statistics probability, different type of approach. We're going to introduce then also the idea of the normal curve. And this is a curve that we are going to be using a lot of because it just happens to be the way that our universe works. It happens to be a frequency distribution that happens again and again and again because of the nature of the universe. All right, introduction to probability. So what is probability? Well, the probability is defined, and we'll start off mathematically just so that you will see something that you recognize. Probability is defined for any outcome as the possible successful outcomes divided by all possible outcomes, right? So when you flip a coin and you say, oh, I got a 50-50 chance of getting heads, what you're doing is you're saying, well, there is one possible successful outcome, which is flipping a head. There is two possible outcomes. You can either flip heads or you can flip tails. 1 divided by 2 is 50%, and that's where you get that 50-50% of flipping heads. So it's the outcomes that you're interested in over all the possible outcomes. That's the probability of those outcomes that you're interested in. So probability is extremely important in statistics, and it gets its own symbol, which is P. And as we're going to see later, this is where you get the P value. So you might have heard, if you ever overhear psychologists talking about research, if you've ever been in a methodology class or classes where they talk about research, they will often mention the p-value of a study. And your inferential statistics rides on that p-value. So you will hear psychologists talk about, oh, well, you know, I ran the data and it was amazing, p less than 0.01. And other psychologists will be like, oh, wow, that's great. What a great p-value. And they'll be like, what about your study? And we're like, well, my study, the p-value was 0.35. And they're like, oh, no, that's horrible. It's a high p-value, right? P-value is very, very important. It's what we base our decisions on in inferential statistics. So you can see why it's important to know probabilities. So that's mathematical probabilities. But for a statistician, probabilities are equivalent. They're the same as proportions. They're the same as pieces of something. So it doesn't matter if you're talking about a specific outcome. It doesn't matter if you're talking about classes of outcomes. It doesn't matter if you're talking about a specific outcome in classes of outcomes. So that's what this notation means. If you ever see this, that means the probability of A occurring. This is when you identify a single outcome. So the probability of A occurring is the number of outcomes that are classified as A divided by the total possible outcomes. That's what we're looking at with probability. So we talk about probabilities and proportions. So what are they proportions of? What are we talking about pieces of? Well, probability for a statistician are pieces of a frequency distribution. It's proportions of a frequency distribution, proportions of that graph that tells you how many people attained each particular possible score. So let's take a look at this so that we can understand it visually. So what we're going to do is we're going to go to the classic probability example, and we're going to take a look at dice rolls and the outcomes of rolling a dice. And these were some of the first studies that were ever done on probabilities. And they started with what is known as Monte Carlo simulations. And that is named after the Monte Carlo casinos where this work was done. And this was way before the advent of computers or computing power. And if you could not mathematically figure out what the probability of something was, or if you wanted to test what the probability of something was, you would go to the casino and you would just watch it being done 1,000 times, 100,000 times, maybe 1,000,000 times, just to make sure what the probabilities were. So there were people in a Monte Carlo casino who were just watching people roll dice, and they'd roll once and they would find out what the raw score is. They would roll it again. They would find out what the raw score is. They would roll it a third time, find out what the raw score is. They would roll it 100,000 times. They would find out what the raw score is, and then they would see what the probability of certain outcomes are. So we don't have to do that now because we have computers that can simulate a lot of these types of studies, but that idea of the Monte Carlo study, just running the probabilities, is still with us. But let's take a look at dice roll outcomes. And let's say that we did do that Monte Carlo study, and we went to the casino, and we found a place where they were throwing single dice. It was a game where you're just throwing one die, right? One six-sided die. What were the outcomes that are possible? What would we have possibly observed? Well, the first thing is that we would have found nobody ever rolled a zero, because zero is impossible. You can't roll a zero. So out of all the times that we saw them roll, not once would they have rolled a zero. But if we were there long enough, we might record 921,541 rolls of a one. So 921,000 times somebody rolled the dice and a one popped up. Maybe 1,042,000 times somebody rolled a two. 921,825 times somebody rolled a three. And then somebody rolled a four, somebody rolled a five, somebody rolled a six, all of those massive numbers of times. And as you can see, it's a fair six-sided dice. Nobody's ever rolled a seven, right? You never roll seven when you're rolling a single dice. So these would be the frequencies that we would be working with. And you'll notice that they're all close to 1 million, right? They're all pretty close to 1 million with a little bit of variation. And if we were able to do this indefinitely, what we would find is that all of these numbers would kind of equalize out if it's a fair dice. And that is reflected in what statisticians like to call the expected relative frequency, where you reduce all these huge numbers down to numbers that we can easily understand, which is the idea that if you were going to roll this dice 6 times, on average, in the long run, on average, you would get one roll of a 1, you would get one roll of a 2, one roll of a 3, one roll of a 4, one of a 5, one of a 6, you would never get 7. So these are they're the same idea. It represents the same probabilities. It's just an easier way to see the numbers. It's an easier way to get our minds, wrapped around it. All right. So those are the outcomes, expected relative frequencies. This is a frequency table. This is a frequency distribution. So now let's take a look at the probabilities. So the probabilities, we're going to do a probability here, so P for probability for each outcome. So the formula for probability is the number of possible outcomes, which is your expected relative frequency, divided by the total outcomes, which is the sum of your expected relative frequencies. So if we were going to calculate the probability of rolling a 0, it would be 0, which is its expected relative frequency, divided by 6, which is the sum of the expected relative frequencies, and you would get a probability of 0. you have a 0% chance of rolling a 0. For a roll of 1, you have one way to roll a 1. There are 6 possible ways to roll the dice. 1 divided by 6 equals 0.17. You got a 17% chance of rolling a 1. You have a 17% chance of rolling a 2, because there is one way to roll a 2, but there's 6 ways to roll a dice. There's 6 possible outcomes. And you'll see that for a fair dice, every single outcome is equally probable. There's a 17% chance of rolling a 5, a 6, a 3. All of those have equal probabilities. All right, so far, math, right? This is the mathematical way of thinking about probabilities. But these expected relative frequencies here, this frequency table, can be made into a frequency graph. So if we graphed it here, and we have frequency, right, this is a frequency distribution, we got frequency on the y-axis, we got possible outcomes on the x-axis there. This frequency distribution is how statisticians think about probabilities. Proportions of this graph, proportions of this area is what statisticians think about when they're thinking about probabilities. So this complete frequency distribution here represents 100% of all the possible outcomes. Anything that can happen is going to happen in this area here. And then whatever you're interested in is parts of that area. So let's see an example of what I mean here. Let's say that you're playing a game. Let's say that you are playing something like Snakes and Ladders. And you have that rule where you have to roll exactly the number that you need in order to win the game, right? You can't do that thing where you just pass, the finish line. You do that part where you have to land exactly on it, and if you don't, you count backwards and end up wherever you end up. Let's say that you're doing that, and you're about to win the game, and you need to roll a 2. A 2 is what you need in order to win the game. What's the probability that you're going to win the game on the next dice roll? Well, there's one outcome that is going to win you that game. It's a 2. There's 6 possible outcomes. So you have a 17% chance of winning that Snakes and Ladders game on your next roll. Statistician, on the other hand, would say, all right, these are all the possible outcomes, all the possible dice rolls. And your probability of winning on that next dice roll, you need a 2. So your probability is that shaded area. That is the probability of you winning on that next dice roll. And that shaded area is 17% of this distribution. That shaded area is 17% of the whole area here. But it's important to know that that blue shaded area, that is what a statistician is interested in. That's how we think about probability. So far so good, but it doesn't really seem to get you much of a benefit, because figuring out one probability mathematically is basically as easy as figuring out one probability in this manner. So where does the usefulness of this come into? Well, it comes into when you start to think about multiple probabilities. So for example, let's say that you were playing a game, and let's say that in this game, you win if an even number is rolled, and your opponent wins if an odd number is rolled, right? So it's almost like a game of war. You're just rolling a dice, and if an even number comes up, you win. If an odd number comes up, your opponent wins. So you win when a 2 is rolled, a 4 is rolled, and a 6 is rolled. What is the probability that you're going to win on any single roll? Well, you're going to win if a 2 occurs, a 4 occurs, or a 6 occurs. And there's a 17% chance that a 2 will occur. There's a 17% chance that a 4 will occur, and there's a 17% chance that a 6 will occur. But what's the probability that any one of those will occur? And that's where it gets a little bit complicated, because what do you do with these numbers? Do you add them all up? Do you multiply them by each other? Do you take them to the power of 3? What do you do with these? You can do a bunch of things with 3 numbers. It can get a little bit confusing mathematically. However, if you think about it as a frequency distribution, those are all the possible outcomes of your dice rolls. You win on a 2, a 4, and a 6. Those blue areas, those shaded blue areas, is when you win. And what proportion is the shaded blue area of the total area? It's 50%. So you can see it's a lot more intuitive. It's a lot more straightforward when you think about probability in terms of these proportions of a frequency distribution rather than in terms of sort of floating numbers and percentages. Any questions on that so far? All right, so let's make it a little bit more complicated. We were looking at one dice. Let's take a look at two dice. So the outcomes or the expected frequencies for rolling two dice are as follows. So impossible to roll a 1, impossible to roll a 13. You can roll a 2, but there's only one way to roll a 2. You got to roll a 1 on the first dice, 1 on the second dice. You can roll a 3, and there's 2 ways to roll a 3. You can roll a 1 on the first dice and a 2 on the second, or you can roll a 2 on the first and a 1 on the second. The most common, the highest frequency, the mode, if you would, is the 7 right here. There are 6 ways to roll a 7. You can roll a 1 and a 6, a 2 and a 5, a 3 and a 4, 4 and a 3, 5 and a 2, or a 6 and a 1. That's 6 different combinations. And then all the way down here to roll a 12, you need double 6s, and there's only one way to do that. So that's the expected frequencies. We can once again calculate their probabilities. Once again, use the same formula of expected frequency, possible outcomes, divided by total outcomes. So there's 36 ways that a dice roll can occur when you're rolling 2 dice. So a probability of rolling 1, 0 divided by 36, 0% probability. Probability of rolling a 2 is 1 way to do it, 1 divided by 36, 3%. So if you land, does anybody here play, has anybody here ever played Monopoly? Okay, so you know the power of the Park Place Boardwalk properties. If you land on Park Place and you're able to buy it, you only have a 3% chance of landing on Boardwalk your next turn and like completing the rental property. So it is rare. It is the rare move to land on Park Place one turn and get Boardwalk on the next. And you can see here, that only occurs 3% of the time. So we can calculate the probabilities for all of these outcomes. And as you can see, rolling double 6s, only 3% of the time. 13 is impossible. 7 occurs, highest probability, 17%. And once again, we can represent this mathematically, or we can take this frequency table here, and we can change it into a frequency graph and represent this as a proportion, represent it as a distribution. So once again, what does this do for us? Well, let's say that we're asking questions about the probability of multiple outcomes once again. So let's say that you were friends with a mathematician, and this mathematician devised a game where in order to win on that final turn, in order to win, you have to roll a prime number, right? You have to roll one number that can not be divisible by any other factor except one in itself. So what are the prime numbers that are possible? Well, you can roll a 2, that's prime. You can roll a 3, 5 is prime, 7 is prime, and an 11 is prime. Those are all the prime numbers that you could possibly roll. What's your probability? If you need to roll a prime number, what's your probability of rolling a prime number? Well, once again, we have that conundrum. We got the individual numbers. What do? We add them all up? Do we multiply them? Do we divide some numbers by the other numbers? What is it that we're supposed to do with this? Do we take the average of all of them? It can get confusing. You put it into a graphical form, put it into proportions. This is 100% of the outcomes. Those are the outcomes where you win. So the blue proportion of this graph is the probability that you will win. The blue section of it, whatever percentage of this entire area the blue section is, that's exactly the probability of rolling, in this case, that prime number. All right, so let's increase this, we'll play this game one more time, just to kind of show you what we can do. So we'll go to Yahtzee now. So 5 dice roll outcomes. So you're rolling 5 6-sided dice. Once again, we got outcomes and expected relative frequency. Those are all the outcomes. Here are the expected relative frequencies. So there's only one way to roll a 5. You got to roll a 1 and a 1 and a 1 and a 1 and a 1. There's only one way to roll a 30. You got to roll a 6, a 6, a 6, a 6, and a 6. There's 735 ways to roll 16. You can roll a 1 and a 2 and a, no, I'm not going to do all of them, but you can see there's 735 ways to roll a 16. we can put this into a frequency distribution. That's what the frequency distribution looks like. And this frequency distribution we're going to see is what we're going to be using in the coming weeks. But importantly, nothing has changed. This frequency distribution here is 100% of all the possible outcomes. And you can see from the height of the bars here, rolling a 30, 5 6s, really, really low probability. Rolling a 5, 5 1s, really low probability. Highest probability are, we got 15, 16, 17, and 18 occur with the highest probabilities. And if you were trying to figure out, well, what's the probability of rolling a number 10 or less? Sorry, make that 12 or less. Well, it's very complicated if you're dealing with the numbers. But what's the proportion of the curve? That's the proportion of the curve. That blue area, whatever proportion it is, that's the probability of rolling 12 or less. If you want to know what you'll get, what's the probability of rolling 23 or more? That's the probability of rolling 23 or more. And if you want to know the probability of rolling 12 or less, or 23 or more, well then it's those two blue areas right there. And all you need to do is figure out what's the total area of this frequency distribution, and then you figure out what's the area of each of these blue areas that you're interested in, and simple as that, you get your probability of those blue areas occurring. You get the probability of those outcomes. All right, so I can tell by your faces you figured it out. That's not easier, right? It's like, why is that any easier? We've just gone from one really hard thing, which is dealing with mathematics, and now you want us to find areas of curved frequency distributions. Bust out your calculus, bust out your derivatives, and let's get down to this. So that would be true if it wasn't for one thing. This frequency distribution here happens over and over and over again because of the nature of our universe. And it has been figured out by people with better mathematical skills than us. And we're going to lean on their analysis in order to do the statistical work that we want to do. So this is approximately getting to the point where it's a normal curve. You might have heard this called the bell curve, right? This is a distribution that happens over and over and over again. And it was discovered and analyzed by Gauss. You'll also hear the term Gaussian distribution. It was also, I think, independently discovered by Laplace. It occurs in nature over and over and over again. And thankfully, because of this, it has been completely analyzed. It has been figured out, crunched, numbers have been calculated. So when I talk about, oh, we need to find the area of the blue compared to the total area, all we need to do, all we're going to learn how to do, and this is going to be in the next coming weeks, is learn how to identify the area that we want, and then learn how to consult all the work that these individuals did in order to get the numbers for that particular area. So we're not going to be calculating, the areas of curves or anything like that. All we're going to be doing is we're going to be identifying what we're interested in. We're going to be understanding that probability is a frequency distribution, but a portion of that frequency distribution. We're going to learn how to figure out, number one, what proportion we're interested in, and then how to find the information to tell us what's the size of that proportion, aka what's that probability. So what we're going to end with today, are there any questions on kind of what our game plan is for the next little bit? All right, so what I'm going to end with today is just a brief look at the normal curve, just so we can kind of understand why is this thing happening so often, and also the importance of understanding why it happens so often, because it occurs in so many instances, especially when you apply things to human behavior, it occurs over and over and over again. And it can be misinterpreted and really lead you to make biased conclusions, biased assumptions, and just justify incorrect ways of looking at stuff. So we're going to make sure that you understand the normal curve so you don't fall for those traps. But first, the normal curve it's a mathematical distribution. It's a theoretical distribution. But the key is that it often occurs in nature. And the normal curve here is that classic bell curve. So if you're talking about a unit normal curve, this is a normal curve made up of z-scores, so that it has a mean of 0 and a standard deviation of 1. That's a very special normal curve, and we're going to be dealing with that normal curve. But really, any curve that forms that bell-shaped curve, regardless of what its mean is or how widespread it is a normal curve, if it has that normal curve shape. And as you can see, this normal curve shape is starting to occur here when we're looking at 5 dice roll outcomes. Those two curves are very, very similar. And the reason for that is because of the reason of why this normal curve occurs. And a normal curve occurs when a number of independent factors all contribute to a single score. So this graph of 5 dice rolls started to approximate a normal curve because the totals here, a total of 10, a total of 20, a total of 24, those outcomes were the combined product of 5 independent outcomes, 5 independent dice rolls. So the first dice was rolled, and it had no impact whatsoever on the second dice roll. The second dice roll had no impact whatsoever on the third dice roll. 5 independent things came together to form this one final score. If you have that situation, you have a frequency distribution that's going to be a normal curve. So this occurs because many of those factors combine to form a normal single score. So let's take a look at this sort of unfold in real time, if my processor can handle it. So this is a normal distribution sort of generator toy that's being illustrated here. So the way that it works is it has marbles, or it has little ball bearings that fall down kind of like in an hourglass situation. And you can see that on the top portion now, when he flips it back, you can see that there's all these little pegs, right? There's all these little pegs that are there in the top portion. And what those pegs do is when a ball hits that peg, it's got a 50% chance of going one way. It's got a 50% chance of going another way. Then it hits another peg, and it has a 50% chance of going one way. It's got a 50% chance of going another way. Then it hits another peg, 50% chance, 50% chance. And what these things do is they make the final position of these ball bearings an independent accumulation of all these little go this way or go that way, go this way or go that way, go this way or go that way. All of these independent events combine to determine where these ball bearings are at the end. And that's why when the ball bearings fall, they fall in this normal distribution. So most of them are going to fall here in the middle, because most of them are going to go a little bit to the left, and then some of the ones are going to send them to the right, and then you're going to get sent to the left again, and you're going to end up somewhere close to the middle. That's the most common outcome. Some of them are going to end up all the way over here, and these are the ones that go left, and then 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 left. And those are going to be very rare to go left so many times. And the ones that end up over here are going to be the ones that are very rare that go right all the times. So you can see that that curve comes about because of the unlikelihood of these independent events all going in one direction, either left or right, and the higher likelihood that some will go left, some will go right, and you'll end up in the middle. But because of this, because of those multiple independent factors that are determining the directions, we end up with this normal curve. All right, so that is something that's very important to remember. Many random factors, and that's why this looks like a normal curve, because each dice roll, many random factors. In this case, we have 5 random factors contributing to the normal curve. But this many random factors is one of the things that is forgotten when people discuss normal curves. It's one of the things that people just intuitively seem to forget, and it's literally the most important part of the normal curve to remember when interpreting any normal curve. So we're now moving towards the final portion of today, which is going to be a sort of applied psychology example, just so that we know that we have those critical skills to take a look at data. Because anytime that you see a normal curve, anytime you see this bell curve, what I want is a little siren going off in your brain that says multiple factors, multiple random factors. Let me not forget multiple random factors, because so many things in our world pop into random scores. So here we have SAT scores in 2010. And these SAT scores, they are contributed by multiple factors. So one of these factors is the intelligence of the student, right? The higher the intelligence, it's going to push you towards this side. Lower intelligence is going to push you towards this side. But other factors are also involved, such as the health of a student. So what's this student's medical history, right? Was this student healthy throughout their entire school experience? That's going to push them this way. Or were they very unhealthy through their school experience? That's going to push them this way. Socioeconomic status, right? Were their parents able to afford tutors? Were their parents not able to afford, tutors? School districts, right? Were they in a good school district? Were they not in a good school district? There are hundreds of factors that go into that final SAT score. And we know there's multiple factors because, again, as soon as you see this, it means multiple factors. The problem is that SAT scores are supposed to measure success in university, right? They're supposed to be predictors of success in university. And people often take those as indicating intelligence as well. And that's one of the reasons why there has been a push recently to correct these SAT scores and give students what's known as an adversity score, basically taking into account that there are multiple factors that cause certain SAT scores, and somebody with factors that work against them, low socioeconomic status, don't come from a good school district, don't have access to high quality education, those factors can lower an SAT score, not indicating that this person isn't going to be successful in university, just indicating that they came from this adverse background. So that is an acknowledgement of the fact that this score here has to do with multiple factors, and this, the people up here, are when all those factors work together. It's when they roll sixes across the board. So they got the DNA, that increases intelligence. They got parents that were invested in them. They came from a good school district. They were healthy most of their lives. They slept a lot, during their formative years. Everything worked in their favor, and they got the super high SAT scores. People down here, everything worked against them, and they got super low SAT scores. Most of us, somewhere in here, right? Some things work for, some things work against, some things benefit, some things, decrease. But it's always important to remember this isn't a measure of one factor. And I mention this because the normal curve has been used improperly in certain situations. So, for example, just to prove this point one more time, heights of various adult women and men, heights of adult women and men. We have women over here and their average heights, and once again, you can see this bell-shaped curve. It's a little jagged, probably because of the number of people that they surveyed, but you can definitely see that normal curve pattern. You can see the men more variable, more widely distributed, but again, that normal curve pattern right about there, that's as of 2007. And this, again, should trigger that warning signal that says, you know what, height has to be a number of different factors. There's not just one factor that contributes to height. And if you look into the research, how to increase your height, there are multiple factors. So for example, genetic factors, they do contribute a large portion, 60 to 80% of your height is determined by genetic factors. But balanced diet contributes, right? You eat a balanced diet, it'll push you towards the taller end. You eat a non-balanced diet, it'll push you towards the shorter end. Use supplements with caution. People that are taking osteoporosis medication like vitamin D or calcium could push you one way, could push you another way. Get the right amount of sleep. Who would have thought? Sleep more, get taller. Sleep less, not as much. Stay active. Things like practicing good posture. I'm trying to read that one, I want to straighten up a little bit. Practice good posture. Using yoga to maximize your height. There's a number of things that contribute to the height that any single person is. And again, we know this because as soon as you see that normal curve, you're like, oh yeah, of course, multiple factors. And I mentioned before, this is why I wanted to get to this. This has been used and abused. The normal curve has been used and abused. And one of the things that you're learning psychology and statistics for is to make sure that you don't fall for any of these traps, to make sure that you interpret the data correctly. Because psychology deals with a lot of very interesting stuff, but some of it can be very sensitive, and some of it can have huge ramifications. We want to make sure that we're getting to the truth. And one abuse of the normal curve came from studies that measured the IQ of different ethnic groups. So here we have the IQ scores of Caucasians, and here we have the IQ scores of African Americans. And as you can see, normal curves here. And this data has been used to argue a number of different things, but the conclusion that is most often reached is that Caucasians just genetically have superior intelligence compared to African Americans. That's where the mind tends to jump to. However, hopefully you can appreciate at this point, anytime you see a normal curve, that means multiple factors. So is the difference there possibly due to genetics? Absolutely. That might be the one factor that is splitting these two curves. Is it due to possibly a number of other factors? Absolutely. It could be due to socioeconomic status in the United States. It could be due to educational opportunities. It could be due to the healthcare system. It could be due to any difference between African Americans and Caucasians. It could be due to any of those. So that idea that you can just jump to a conclusion based on this ignores the fact that as soon as you see that normal curve, it's multiple factors. So role of IQ, modifiable environment factors like education, premature birth, nutrition, pollution, drugs and alcohol abuse, mental illness, and diseases, they can all have an influence on individual level IQ. So there's a difference here. You know, that is something that is in the data, but why that difference is something that we as statisticians need to figure out. And again, all of these other factors could be the reason why that difference is there. And it's very important not to jump to conclusions because that is often what is done when people have access to data like this. All right, so that's all that I wanted to cover for today. So I will be populating my lab with the assignments either today or early tomorrow. So keep a lookout. The pretest for chapter 4, I never want to assign a pretest the class after an exam. I kind of feel that's a little cruel. So this was just a little breather after the exam, but there will be a pretest on chapter 4. You got a little bit of a preview on that. But I will be populating the rest of the assignments. I'll be grading your exams and sending those back as soon as I can. But don't forget about the pretest points. And again, those any pretest points, any pretest that we do now, you can do the MyStat Lab study plan to earn pretest points for those up until the day of exam number 2. So that's all that I want to cover for today. We don't really have a lot of past stuff to practice, so if you have any questions, call me over, let me know. But other than that, feel free to call it an early day.